Good morning. Thank you guys again for your patience this week. This surgery that one of my sons had was supposed to be done right before spring break so that I would be home with him that whole week while he was recovering. And then it got bumped a week. So they pushed it to the end of last week, which meant, we were scrambling to try to figure out how we were going to manage that. So I appreciate you guys being patient as we have to do, multiple video lectures, especially right after spring break. I realize that's difficult. Like I said in the email, though, the plan is that I kind of push the schedule a day, everything moving forward a day, so that we can use Friday just for reviewing chapter 14, because half of it we did before spring break and then half of it we did via video. So I know that that's a little bit hard. So we'll just spend Friday reviewing, and then the chapter 14 homework will be due on Sunday night, and the prep for 16 will be due Sunday night, and we'll go into next week doing chapter 16, okay? I put a new schedule on Blackboard. I really shouldn't say the date without checking. Let me just look really quick. But the next exam, just so you kind of have your eye out for what's happening in the schedule, the next exam will be the 11th of April. Okay, so April 11th is our exam 3. Okay, so it's nice. Today's a little bit of a light day. So yesterday was very heavy. I know we had that big review stuff in that first part, and then we had the new material, which was a lot of calculations, and I know probably was a bit difficult in some respects for those of you who aren't in love with math. So this one's a little bit lighter, but it also practices some of the things that we did, the math stuff that we did last class. So I think it'll be a good mix. It'll probably be a bit shorter, maybe only like 30 minutes or so, versus the, hour plus that yesterday's was. So hopefully that'll even things out a bit. Okay. So the big topic that we're talking about today is colligative properties. And what this means is that there are certain properties that change based on whether you have a pure substance like water versus if you have a solute added in. So water plus NaCl or water plus sugar, this is going to have an effect on these properties. So the properties that we're talking about here, there's 3 that we're going to address, is freezing point. I was trying to see if these equations, they don't exactly correlate, so I'll write it down here. So freezing point, boiling point, and osmotic pressure. Now, osmotic pressure is one that you're probably familiar with if you are a biology student. It actually has a lot of environmental, like plant relationships too. But there is a pressure that develops when you have a different concentration, 2 different concentrations next to each other. So like a pure thing and something that has a solute in it, or something that's very dilute and something that's very concentrated. So we'll do that one last. But we've talked a lot about freezing point and boiling point. And what we're talking about here now is that when you add a solute or you create a solution, like in these 2, that is going to have an effect on the freezing point of that substance. So water is going to freeze at a different temperature than water with salt dissolved in it. It's also going to freeze differently depending on how much salt is in it. Okay? Same thing with boiling point. All right, so these 3 equations, this one correlates to freezing point, this one correlates to boiling point, and this one correlates to osmotic pressure. These are the 3 equations that we're going to use to determine how those freezing points and boiling points and osmotic pressures change based on the amount and the substance that we're dealing with. So before we get into the specifics, let's just look at kind of some similarities here. So the first 2, boiling and freezing changes, we are going to calculate those using the molality of the substance. Okay, so that's the first thing, is that you're going to have to make sure that whatever solution you're talking about, you convert it into molality, which this is review from last class, but that is moles of solute over kilograms solvent. So I think even in the first example problem that I have coming up, we are given the concentration of the thing, not in molality. It's given in like percent by volume or something. And so we have to convert that into molality before we can use this calculation, before we can use this equation. Okay, so be aware of that. These two, Kf and Kb, those are constants that are specific for whatever substance you're talking about. So you would have to be given these individually in every single problem. So there is a Kf associated with water. There's a Kb associated with water. There's a Kf associated with oil or an alcohol or anything like that has its own specific Kf and Kb. Now, most of the solutions we deal with are aqueous, meaning they're water-based, and so those are going to be frequently, these are going to be the Kf and Kb for water, but in theory, you could do it for something else as well. And the last part of this equation is the I that's listed here, this little lowercase I. That has to do with ions in an ionic solute. So for now, all I want you to know until we get to the end of class today, all I want you to know is that I equals 1 if it's a covalent compound. Okay, and then we will get into what it is equal to for ionic compounds later. But if we're talking about sugar or alcohol or oil, those would all be covalent compounds, and I would be equal to 1. If it is a metal and a non-metal, an ionic compound, then we have to do something different. Okay? So when we combine I, molality, and this constant, it tells us the change in the freezing or boiling point, meaning does it change 5 degrees from what it was originally, or does it change 2 degrees? Okay, so that's what we're going to be calculating. No, I don't want to scroll to that yet. I want to say a couple more things. I wasn't sure how much detail was on the next one. Okay, so another note that I want you to be aware of is that change is going to be, for boiling point, that's going to be an increase in the boiling point when we add a solute. So when we add salt, like let's use pasta for an example. You're cooking a pot of pasta. You put salt in to the water. It is going to increase the boiling point so that when you are boiling the pasta, it is actually not at 100 degrees Celsius anymore. Maybe it's at like 101 or 102. Okay, so it's actually interesting. It causes the pasta to cook a little bit faster. But it's such a small difference that you would never notice it. But like in theory, if you were to put salt in, maybe it would shave off the cooking time by like 30 seconds or 20 seconds or something. It's not enough to make a difference, so nobody worries about it. Okay. For freezing point, we see a decrease in now we call this melting point usually, right? But that would be synonymous with freezing point, okay? The temperature at which water, let's say, freezes, right? So water freezes at 0 degrees Celsius. So if you were to add salt to water, you can get it to freeze not until maybe -5 degrees Celsius or maybe even -10 degrees Celsius. And this is why we use salt on roadways in order to prevent precipitation, snow, or rain from freezing, so that it's safe driving conditions. So we add salt, it decreases the freezing point of the water, and so that water then doesn't freeze and keeps the roads clear. Okay, so now we're going to go ahead. That's the basic overview of how these work. You can always review in the textbook, if you need another explanation of it. But that's what we're talking about. We're talking about these freezing and boiling points. So we're going to come back to osmotic pressure later in class. For right now, we're going to focus on freezing and boiling, and we're going to do calculations with them. All right, vodka is ethanol and water. We have a sample of vodka that's 35% by mass. Okay, so they're telling us the concentration, but it's percent by mass. So we're definitely going to have to do a calculation that's similar to what we did in the last class, where we're going to convert this into molality, because that's the thing that our equations are using, right? So that's kind of the first thing to be aware of. That density that they give, we're going to need that in order to do that conversion. Well, wait, are we? Oh, you know what? I actually don't think we will need that for this one. That's nice. So sometimes they give you that information because we would need that if we were, say, converting it into molarity, which is actually, I didn't mention this, but that's what you use when you're doing osmotic pressure. So change in freezing point and boiling point, that's in molality. Change in osmotic pressure, that's molarity. If we were doing molarity, we would have to have the density. For molality, we won't actually. So we'll do that in a second. Okay. So before we get to doing that conversion, let's just kind of set up our two equations here. So what is the freezing point of the above solution? So we know, I expect you to know that water's freezing point is 0 degrees Celsius and its boiling point is 100 degrees Celsius. Okay, so keep that in mind. You'll have to know that. This one asks, what's the freezing point of the above solution? So freezing point decreases when we add a solute. In this instance, the ethanol is our solute that we've added into the water. So the water ethanol solution is going to have a freezing point lower than that of water. So it's not going to be equal to 0. Is going to be some value lower than that. And the number of degrees lower that we're going to determine how much lower it is by. So is it -2? Is it -5? We're going to do that from this calculation. So the change in temperature of freezing is equal to IMKF, where in this instance, I is equal to 1 because it is a covalent compound, ethanol. M is what we're going to figure out, so I'll just kind of leave a blank there for us. And KF here is given as 1.86 degrees Celsius per molality. Okay, so the little m. So the molality here will cancel out and we'll just be left with degrees Celsius. Now, remember, keep in mind that this is a change in temperature. So this isn't actually the new temperature. This is how many degrees it changes by. So is it going to drop 2 degrees? Is it going to drop 10 degrees? That's what this is going to tell us. Same thing when we do the boiling point one. Okay, so before we get started, let's go ahead and do this conversion to get the molality from that 35% by mass. I'm going to move this just to give us a little bit more room. Let's see, where can I move that? We'll put it over here. And we're going to do this conversion from 35% by mass to molality up here in purple. All right, so 35% by mass. Let's define that like we did yesterday. Percent means per 100, century, okay, 100. So 35% by mass is 35 grams of ethanol per 100 grams of the solution. Or another way of saying that is 35 grams of ethanol over grams of ethanol plus grams of water, knowing that those have to add up to 100. So we said it's 35 grams of ethanol. We already have that amount. And so we just have to know the difference now, or 65 grams of water. Okay, so 35% by mass means 35 grams of ethanol for the total 100 grams of solution. If 35 of it is ethanol, that means 65 of it is water. And so, either one of these are all equal to each other. This is all equal to 35% by mass. We're just kind of breaking it down and defining what that really means. Okay, why do we do that? Because now we have to convert it to molality. So I'm going to do that in green. So molality is moles of the ethanol per kilogram of water. Because remember, molality is kilograms solvent, whereas like molarity is liters solution. So be clear, there's a difference between solution, that would be the solute plus the solvent, versus the solvent itself. In this instance, it's just the water. Okay, so like yesterday, or Wednesday rather, Monday, oh my goodness, my days are getting so confused with not going into work. So moles of ethanol, we're going to use this 35 grams and we're going to convert that to moles. And then that's going to go on top of our molality calculation right here. And then on the bottom, we're going to have the kilograms of water. So we're going to convert 65 into kilograms, and that'll go on the bottom. Then we divide moles by kilograms, and that's our molality. Okay, so I'm just going to erase this part here so I have some room. So 35 grams into moles. The way that we're going to do that, I never know if I should rewrite it or not. I think I'll just erase this and start from here. So 35 grams of ethanol, we're going to multiply that by the molar mass to get it into moles. And the molar mass of ethanol, somewhere around like 40, so 12.01 times 2 plus 1.008 times 6 plus 16. So it's 46.068 grams per mole. So 35 divided by 46.068 is 0.7598. I'm going to go that many sig figs. I probably could have stopped at 0.760, but I'm just going to go there. Okay, so this is moles. And then kilograms, we just need to divide by 1,000. Okay, so this is equal to 1,000 grams for 1 kilogram, or 0.065 kilograms of water. And this is moles of ethanol. Okay, so now we need to just plug in here 0.7598 moles over 0.065 kilograms. And that is equal to, that is a big molality, but 35% is pretty darn concentrated too. So since this is 2 sig figs, I'm going to give myself 3 just to be sure, but not a big deal what you end up doing. So 11.7 molal. So that number is going to be plugged in here. 11.7. So when I calculate this out, I get a change in the freezing point of 21.8 degrees Celsius. Okay, that means that this ethanol water mixture is going to drop to negative 21.8 for its freezing point. Because it doesn't say what's the change. It says what is the freezing point, like what's the new freezing point. So if water started at 0 degrees Celsius and we know that freezing points drop, then the new freezing point is negative 21.3 degrees Celsius. Okay. I'm not a big alcohol drinker, but I do know that people often store vodka in the freezer. This is why you can do that, because and it doesn't freeze, because it is typically freezers are kept around like negative 10 degrees Celsius, I think. I'm trying to remember if mine has, I don't think mine has a gauge on the little screen thing. So it's not going to freeze even at freezer temperatures. Okay, so the one for boiling point is going to be really similar, but remember that boiling points go up. So it's going to be, we're going to do this calculation and then we're going to add that to 100. So 100 is going to be our starting point, and we're going to add whatever the change in temperature boiling gives us, and that's going to be our new boiling point. So change in temperature boiling is equal to IMKB. So this is a different constant. So it's still 1. We already found out the molality, 1.7 m, and 1.86 degrees Celsius per molal. Okay, so 11.7. Oh, sorry. I said it's a different one, and then I just kept going. 0.512. Let's give it right here. Okay, so 11.7 times 0.512. So the change in boiling point is 5.99 degrees. So the new boiling point is basically 106 degrees Celsius. Okay, freezing points go up. Sorry, freezing points go down. So you subtract whatever you get from 0. Boiling points go up. So you add whatever you get to 100. Looking at what we have here. Oh, those are both. Okay, so now we need to talk about ionic compounds. So KNO3 is an ionic compound. So now we need to talk about what changes with I. So the reason it says assume complete dissociation of the solute, it means that when we stick KNO3 into water, you've got to remember that this breaks up into K plus and NO3 minus. Because of that, these two things behave twice as effective as a covalent compound would, because there's 2 of them. It almost like doubles the number of moles of solute you have. Now you still just have, like, let's say you were adding 1 mole of potassium nitrate, you still have a mole of potassium nitrate, but because they break up, you now have 2 moles of solute, because you have 1 mole of K plus and 1 mole of NO3 minus. Okay, so in this instance, we have to account for that by multiplying our whole equation by 2. So in the example of KNO3, I would be equal to 2. And this is going to be the case with any ionic compound. So let me just kind of address another example, and then we'll come back and do this problem. So let's say magnesium chloride. If that dissolves into water, you should remember that that breaks up into Mg2 plus, Cl minus, and Cl minus. So in this instance, I would be equal to 3. So really, it's just the number of ions. It's easy if there's no polyatomic ions. If there's no polyatomic ions, then you just count them up. 1 magnesium, 2 chlorines for a total of 3. If I had like lead, This isn't really a common compound at all, but let's just pretend. If I had lead 4 chloride, that would be 5. Okay. Where it usually throws people is when they're polyatomic ions. So like sodium sulfate. So there's 1 sulfate. That only counts as 1 because it doesn't break up when it gets into the water. It separates from the sodium, but the sulfate doesn't separate itself. So this is not, I does not equal 7 here. I is equal to 3, okay, because it would be 2 sodiums and 1 sulfate. Okay, so I'm going to delete that. We're going to go back to this problem. Assuming complete dissociation, so I is equal to 2 because it's potassium nitrate, how many grams, okay, so this question is asking us something different, must be added to 275 mils of water to produce a solution that freezes at negative 14.5 degrees Celsius. Okay, one more piece of information they didn't give you that you're going to need is that the density of water is approximately 1 gram per milliliter. Okay, you can just know that if they don't give you a, because it does change with temperature, so like it's either slightly above or slightly below that. If they don't give you that, you can just assume that it's 1 gram per milliliter. If it's not on a test, ask me and I'll remind you, but I do try to put that on there for you. Okay, all right. So they're telling us that we already know what the new freezing point is. It's negative 14. So in this equation of delta TF equals IMKF, they already are telling us that delta T is 15.5, or sorry, 14.5. Okay, because that's the change in temperature from the original. It dropped by 14.5 degrees. Why did I take off the negative? Because they're not telling us to plug in the new temperature change here. Sorry, the new temperature. They're telling us the change. So the old one was 0. It dropped 14.5 degrees. So we just need, excuse me, we just need to know that that's 14.5 from the original. Oops. Okay, so what are we going to do with that information? Well, they're asking how many grams in a certain amount of water. So we're definitely going to have to calculate the molality here, and then we're going to have to figure out how to answer their question from there. Okay, so let's just start by calculating the molality. Maybe on a test, I would break this into an easier question, and I would just say, calculate the molality of this solution. In a practice problem like this, I like to incorporate multiple parts. So the things that we did yesterday where we're doing conversions between different concentration units and where we're doing this new concept of freezing point depression. Okay, so I is equal to 2, M is what we're solving, KF is 1.86 degrees C over molal. Okay. So I need to rearrange this equation. M is equal to 14.5 over 2. So just simple algebra here. Okay. So M is equal to 14.5 divided by 2 divided by 1.86. So the molality is 3.90. Looks like. Okay, so we've determined the molality, but the question wants to know how many grams of this potassium nitrate need to be added, okay, for this 275 mils. So let's do the thing we did before. Let's define the unit. Molality, I'm going to scooch this stuff over. Since this is only our first half of the question. So molality is equal to moles per kilogram solvent. So I'm going to define this 3.90 moles of potassium nitrate per 1 kilogram of water. Okay, and remember, if we have unit over another unit, that's like a conversion factor. Okay, so trying to see where I'm going to put this. So I'm going to go up top here. I'll continue it in green. So how many grams? So equals the number of grams. We're starting with 275 mils. And we're looking for grams, and we're going to use this guy as a conversion factor. So how do I use the milliliters and get to kilograms? Because remember, this is milliliters of water. This is grams of potassium nitrate. So I'm going to have to use this kilograms of water to get me to moles of potassium. I'm going to have to move this down. There's totally not enough room here. I don't know why I ever think that I can do more than one question on a page. Okay, we're going to have to convert from milliliters to kilograms to use this conversion factor. So let's start there. So like I said earlier, the density is 1 gram per mil. So I'm going to use that. 1 milliliter equals 1 gram for water. Then I'm going to convert to kilograms. Then I can use this conversion factor from above and say 1 kilogram, 3.9 moles of potassium nitrate. Okay, so I'll fill in this over here. And all of those units now cancel and give me moles of potassium nitrate. The question doesn't ask for moles, though. It asks for grams. So I need to do a mole to gram conversion. And that will give me my answer. And then in a second, we'll just, describe what that is really telling us. Okay, so potassium nitrate's molar mass is 101.11. 275 divided by 1,000 times 3.9 times 101.11. So this comes out to be 108 grams of potassium nitrate. That's quite a bit of potassium nitrate in really just 1 cup of water. Okay, so what does this mean? It means if I want to lower the freezing point by 14.5 degrees Celsius, which is a whole lot. But if I want to lower it by 14.5 degrees Celsius, I'm going to have to add 108 kilograms of potassium nitrate to 275 milliliters of water, which a cup is like 240 milliliters. So a little bit more, 1.25 cups. I'm going to add 100 grams of potassium nitrate, which is probably a couple tablespoons of salt, to be honest, of this salt, not sodium chloride salt, but potassium nitrate. Okay, and then when I do that, I mix in that 100 grams into the 275 mils of water. It will dissolve because potassium nitrate is very soluble, and then it will lower the freezing point by 14.5 degrees Celsius. All right, so let's go ahead and do, you know what, this is a great one for us to do on Friday. So let's see, how do I want to note that? Because I know I have a few that I said we were going to do that with, and those are all really good ones for Friday. So let me just circle this guy, and we'll come back to that, because I told you it was going to be half an hour, and it hasn't been. We're going to bring that one to Friday as well. And then I want to do 2 of these 3 osmotic pressure. So let's do the first two and we'll save this one for Friday. Okay. So osmotic pressure, like I said, is a force. Pressure is a force that exists that drives liquid to balance itself out, basically. So like if you have a way for water to move through, it's called a semi-permeable membrane, and you have a concentrated solution and a dilute solution. So in this instance, it's literally just salt in water. So you have very salty water on this side and not so salty water on that side, but you have something that allows water to move through. The water will always move. Oh, I drew the arrow I wrote the words the wrong way. The water will always move to balance out those two solutions. So water is going to move from the dilute thing to the concentrated thing. What that'll do is that will decrease the concentration. So it will make this side more diluted. Okay, so that's the reason why this happens. The pressure, the force that causes that movement of the water is the difference in concentration between these two, and that is called osmotic pressure. So in these calculations, we're actually looking at a pure substance and something that has a solute in it, and we're asking what is the pressure that exists between those two that ends up driving the water to move to the more concentrated solution. Okay, so the calculation for this is, I don't think that is actually pi. I can't remember if that's the, pi looks like this. I don't think that is. It's like a straight across. I'm going to have to look up now what Greek letter that is, because I think it is not pi in the equation. Yeah, this one here. So that is the symbol for osmotic pressure. And then you can see the equation here. I, same thing as we were doing before. It's 1 if it's a covalent compound, and it's multiple, depends on the number of ions that it breaks into. NaCl, in this case, I is equal to 2. Okay? Times the molarity, not the molality, the molarity, times R, which this is actually the gas law constant, times T, temperature, okay? So I in this instance is 2. We're going to calculate, we'll do that separately. We're going to calculate the molarity. R is 0.0821 liter atmosphere per mole Kelvin. The moles and liters, that's what molarity is, moles per liter. That'll cancel out. The temperature will cancel out over here. We're going to convert that into Kelvin. And then what we're left with is atmospheres. So that is the pressure unit that we use to describe osmotic pressure. Okay, so temperature first. Kelvin temperature is 273, technically 0.15. I'm going to leave it off because the 25 isn't that accurate. So this is 298 Kelvin. Okay, and then for the molarity, molarity equals moles, NaCl, again, defining it and then solving for it, per liter solution. Okay, so the moles we're going to get from here, 0.923 grams sodium chloride. I'm going to convert that into moles. It's funny how often you do things like sodium chloride and yet I still don't remember the exact molar mass. Oh, see, I thought it was closer to 40 and it's 58. Okay, so 0.923 divided by 58.44. 0.0158 moles. So we'll put that in here, 0.0158 moles. And the liters, 100 mils is equivalent to 0.10 liters. Okay, so the molarity is just 0.158 molar. So we're going to plug that in down here, 0.158 molar, and solve out what that osmotic pressure is. So I get that this is 7.73 atmospheres. Just double checking my work here. Okay, so that is the osmotic pressure of this saline solution. Same osmotic pressure as blood. Fascinating. This is why you don't want to have water pumped into your blood, or else you're going to create a pressure gradient that's going to drive water into your cells, and you're going to get kind of bloated. Okay, last one, I promise. Okay, osmosis is the process responsible for carrying nutrients and water from groundwater supplies up to the upper parts of trees. This is fascinating because I love plants. The osmotic pressure required for this process can be as high as 20 atmospheres. What would be the molar concentration? So they want to know the molarity of the tree sap to have this be achieved when the temperature is 23 degrees. So I don't tell you this here. Tree sap is covalent. It's basically sugar. So I is going to be equal to 1. So the osmotic pressure, they're telling us, might need to be as high as 20.1 atmospheres. I is equal to 1. The molarity is what we're solving for. R and T is going to be 296 when I convert that into Kelvin. And now I can solve for the molarity. So 20.1 divided by 0.0821 and 296. Okay, that's going to tell me the molarity that the tree sap needs to be to drive the water up into the upper parts of the tree. Wow, that is not nearly as concentrated as I expected. I thought it was going to have to be much more concentrated. So 0.8 molar, probably sugar is what it really is, concentration of sugar in that water that's within the tree, so that the water from the ground gets pushed up to, basically it's like driving it to dilute the tree sap. But in the process, it brings nutrients and stuff with it. I like this because most osmotic pressure examples are medical, but this one's obviously very applicable to like environmental stuff, which I know quite a few of you are studying. Okay, so we will do review on Friday. I'll go back through the notes and look at all the practice problems that we didn't do in class, and we'll pull those out and do those individually, and then if there's any others. What I would ask is please do all the studying you need to on this chapter. Please do not wait till Friday to like think that I'm just going to be able to explain 4 days worth of class in one class period. That's not going to happen. So make sure you've watched all of the lectures. I even recorded the ones that were the week before spring break. So literally you could go back and watch the entire thing, all the lectures related to chapter 14. And then note any questions you have, because that's probably where I'll start, is say, what questions do you guys have? And then try to do as much of the homework as possible. If you're understanding these video lectures, you could finish the homework and be done and just, kind of fill in any gaps on Friday, but you could be completely done as of today's material. But it's not required to be completely finished due until Sunday night. Okay, so I expect you to come in having studied the entire chapter, started on the homework at least, done as much as possible. Come in, we'll do more practice problems. I'll answer any questions, and then we'll move on to 16 on Monday. All right, thanks again, everybody, and I will definitely see you on Friday. It is for sure Daddy's turn to stay home with the kiddo. Thanks. Bye.